Okay, so last time we looked at the effect of distributed loads. Okay, and so what I'll do today, and this is really going to be the last lecture on this topic, okay, on the topic of static structure analysis. We're going to start with dynamics during the next lecture, and then we're going to go to the next set of notes, okay, that actually I put together. But I'll just show you how to put everything together. It should also help you do your the homework that I just assigned. Okay, so the problem we're gonna concentrate on kind of has all the elements of what we need to know. Okay, so let's start. All right, it's let's go to page 514. And I'm gonna bounce around a little bit. I'm gonna define the problem and then we're gonna sort of work through it. And here you have a structure that looks like this. Okay, 3 nodes. Okay, these 2 are fixed. Okay, cantilevered. There's nothing much left. Okay, this is node 1. This is node 2. This is node 3. This is element A. This is element B. Okay. So the problem has dimensions. This guy is 10 feet. This guy here is 20 feet. Okay, so and the height is also 20 feet like this. Okay. Now we're going to assume that the Young's modulus is 29,000 kilopounds per square inch, KSI. Area for each beam column is the same. Okay, and the cross-sectional moment of inertia is 310. And the dimension here is inches to the 4th. Okay, so what I'll do is I will apply a uniform distributed load like this. Okay, pointing vertically, and then I'm going to distribute another load, same magnitude, same direction. Okay, so in both cases we're going to get 1.5 kilopounds per inch. Right, same here, 1.5 kilopounds per inch, right? But note that while for element B, the load is pointing directly transverse to the axis of the beam, okay? For element A, the load points in the direction oblique to the beam, okay? So I'll show you how to handle a situation like this, right? And of course, what we'd like to do is resolve the structure, right? We're going to solve for the displacements for UF, okay? Look at support reactions. Okay, and we'll look at the distributions of forces and moments. Forces and moment distribution. Okay, and so kind of I'll take you through this and then you should be able to do it on your own. In fact, if you look at the homework, okay, I'm asking you to do this problem in MATLAB, okay? So you will use this problem to verify your MATLAB code on this problem. Okay, good. Yeah, so you can solve it by hand, and again, there's a lot of information on the notes, and then you want to make sure that your code delivers to you the same solution as the by hand solution, and then you're confident that you can handle bigger and bigger problems, as we will toward the end of the class. Okay. So let's go back. All right. Go to the start, and then we're going to first develop the structure stiffness matrix. Okay. This takes us to page 434, okay, where the structure is first introduced. Okay. All right. So first thing to do is to number the degrees of freedom, right? The DOFs. Okay. Let's do that. This is node 1, right? This is a node 2. This is a node 3. This guy is fixed. And this guy is fixed, right? So then there are no 3 degrees of freedom at node 1. Node 2 would have x displacement, right? Y displacement, and u3 will be our rotation here, okay? And then again, no 3 degrees of freedom at node 3, right? So then we'll label the restraint, guys, and so this becomes u4. This becomes u5. The rotation here becomes u6, u7, u8, and the corresponding rotation is u9. Okay. So we can say that our UF is u1, u2, u3, right? And then the restraint vector has the remaining unknowns, right? u4, u5, u6, u7, u8, and u9, like this. Okay. Good. Okay. So as the next step, right, we're going to develop our stiffness matrix. KFF. Okay. We go element by element. We take element A. Okay. For element A, it's this guy here. This is element B. Okay, the geometry I presented before. Okay. So delta X is 10 feet. Delta Y is 20 feet. Okay. And we can directly convert to inches, right? Because we're going to solve our problem in inches. 240. Right. We compute the length the usual way. 268.33 inches, and then sine and cosine become 0.44721, 0.89443. Okay. So this information allows us to construct what? Gamma RBM, right, for element A, and gamma ROT for element A. Okay. Now for the expressions for gamma RBM and ROT. Right, I'm going to point you to the top of page 435. Okay. Kappa sub A, right? K sub A, element stiffness matrix, is gamma ROT A transpose, gamma RBM A transpose, matrix, a basic stiffness, right? And then we continue the multiplication, gamma RBM A, gamma ROTA. Okay, so this is the product that you need to carry out. Again, you probably shouldn't be doing these things by hand. You do this with MATLAB. Okay, and then you end up with something. Okay, all right, and the relevant entries that you're going to need, okay, are going to be dictated by what? The ID array. Right? So if we take ID for element A, all right, let's scroll back and go back to our structure, right? And you see that if this becomes the direction of the element, right? Delta 1, delta 2, delta 3 point to no equations. Delta 4, delta 5, delta 6 point to U1, U2, U3. Right? This allows us to record the ID array directly. 0, 0, 0, 1, 2, 3. And again, at this point, you've done enough problems to do this more or less automatically. Right? So as a result, right, the only contribution that's non-zero is here. Right, you're going to have a 3 by 3 block, and that 3 by 3 block will directly go to KFF. Okay. And so again, for the exact expressions, I urge you to look at page 36 here. 436. Okay. Good. For element B, okay, what you're gonna find is delta X is 20 feet, okay, or 24 inches. All right, delta Y is 0. Okay, the element happens to be flat in feet or in inches, of course. L is 240 inches. Okay, so this is not 24, this is 240. Cosine is 1, sine is 0. Okay, which implies that the rotation matrix for element B is exactly a 6 by 6 identity. Okay. A direct computation, right, of K for element B, right, results in gamma ROT for element B, which is an identity matrix, times gamma RBM, which is not. Okay, the basic stiffness, K prime for element B, okay, times gamma RBM for B, times gamma ROT for B, which is also an identity. So fewer things to compute. Okay. Right. And what you see is now you can draw the matrix. Right? You can write the ID array on top. Okay. If we go back to our structure, right, this is our element B. Okay, Delta 1 points to U1, delta 2 to U2, delta 3 to U3, right? Delta 4, 5, and 6 point to nothing because at node 3 there are no free degrees of freedom. Okay? So in this case, the ID looks like it's 1, 2, 3 here, 0, 0, 0, and then 1, 2, 3, 0, 0, 0, like this. Okay? So you sort of partition your matrix. You have a 3 by 3 block. Okay? And these are the 3 by 3 guys that go directly into KFF. Okay? In the additive fashion. Okay. And so then you find that your KFF equals 2. Okay. 1. Probably no need for me to record the entries. Okay. Becomes a 3 by 3 matrix. Fully populated. Okay. And you find the expression for that matrix on page 437. Okay. So at this stage, KFF is set. Okay. Let's develop the right-hand side, right? The force vector. Okay. Okay, just a minute as I'm scrolling up on the notes because I'm going directly for the case of an oblique load. Okay. Almost there. Here we are. Okay. So as I said, right, we have a situation where we're going to apply a vertical load everywhere on the structure. .5 kilopounds per foot. Okay. And we're going to apply 1.5 kilopounds per foot here. Okay. So in general, how do we handle situations like this, right? Well, if we look at an element like this, right, and this is what we covered in the previous lecture, right, we can compute the force, okay, the applied force, the equivalence of the nodal forces to that distribution of the load, okay, as follows. Nothing makes it into x, right, because the load is purely vertical. Then we get minus W, right, which is the amount of force per unit length that's applied, multiplied by the length of the beam, right, divide by 2. So the first node gets half the load, right? The equivalent moment, okay, that the first node gets becomes like this, over 12, right? WL squared over 12. Nothing goes into x, minus WL over 2. The second node gets the second half of the load, okay? And the corresponding moment here is positive, and is WL squared over 12, okay? Like this, okay? So this is the vertical case. Okay. What about the oblique case? All right. So in this situation, right, you have some load, okay? Let me orient it, okay, this way. I'm gonna call it W, okay? And that W can be decomposed into two parts. Okay. The part of W that's acting in the x direction, sub x, right, in a local coordinate system, x, right, This is y. This is y, right? And then a part of w that's acting in the y direction. Okay. I'm going to call it w sub y. Okay. And in this case, all right, because we're dealing with linear structural analysis, right? The effect is additive. Okay. We can write the following expression for the force vector in the local coordinate system. Right. And also recall the truss element here. Right. So what you find is for this situation, in the x component, you actually put the x load. Okay, Wx L over 2. In the y direction, you put the Wy. Okay. And so the two are derived. It's interesting how the first one you derived for the truss, right? The second order differential equation, it gave you that distribution of equivalent nodal loads. The second one, you derived it from the beam differential equation, where you went through the moment, you computed the forces by differentiating the moments, okay? Then you went to the ends, right? And you found what the equivalent forces are at the ends, and you get the same result, okay? It's just Wx is swapped for Wy, okay? So what we're doing now, we take in the oblique load, okay? And we're simultaneously account for the vertical action and for the axial action, okay? So we're combining the developments we did for the truss and for the and for the beam column, right? So truss and beam column combined. Okay. So Wx ends up acting in the x direction, Wy and y, okay? It's only the Wy part that contributes to the moment, so we write it like this, Wy, L squared over 12, okay? Then we write minus Wx, L over 2, minus Wy, L over 2, okay? And then Wy, L squared over 12. Okay? And so this is how you handle an oblique load. Okay? Good. Okay, so if you follow the notes, right, page 515, okay, right, what you find, right, is once you introduce sort of your projections, right, if you have 1.5 kilopounds per foot, okay, and the geometry that we use, right, we get a situation like this, where the x component becomes 0.67 kilopounds per foot, right? And this one would take 1.5, right, and multiply by the sine, right, of the resulting angle. Okay. Sorry, not the sine. The sine of the resulting angle, sine phi. Okay. And then plus, we get this guy. Okay. We have the vertical component of the load. Okay. It ends up being sorry, no, this is not 0.67. I apologize. Sines and cosines. Okay, we get exactly 134 kilopounds per foot. and this is 1.5 times sine phi. And here we get 0.67 kilopounds per foot. Okay, and this is 1.5 times cosine phi. Okay, so just a simple decomposition of the vector into the x and y components. Good. And so then once we know that, okay, we can directly come up with the expression for the equivalent forces for element A. Okay, and again, I point you to page 515. 15, right? We're applying the formula that we just developed for F prime F. Okay, don't forget to convert from kilopounds per foot to inches, right? And so you also need to convert feet to inches. Okay, you end up with the expression, okay, that looks like this: 1498, 749, 335, 1498, 749 minus 335. Okay, this is kilopounds, kilograms, kilograms, inch, kilograms, 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 inch. Okay. F prime F for element B, also on the same page, right? There are no forces in the x direction. Okay, so we end up getting 0, 15, 600, 0, 15, minus 600, and this is kilopounds, 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 inch, kilopounds, 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 inch here. Okay. Okay, now in the global coordinate system, contribution from element A, okay, can be obtained by taking the rotation matrix A multiplying by F A prime F, okay, and if you carry out that multiplication, an interesting thing happens. You get back 0. 16, 7, 4, 8, 335, okay. 0, 16, 7, 4, 8, and minus 335 kilopounds, 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 inch, kilopounds, 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 inch. Okay, so note, right, as you would expect, right, after all the geometric transformations, right, no nodal forces in global x direction. Okay, the reason for that is because you did not apply any forces in x. Okay, so it all sort of works out at the end of the day. Okay, FB equals, in this case, F prime FB, because gamma ROT B is the identity. 6 by 6. Okay. Right, so P of 0, right, is what? Okay, you have 3 entries, right? And what you see is the element, right, F prime F for element A, right, will contribute its bottom 3 entries here, and from B will contribute its top 3 entries there, okay, because of the ID, right? And this is 1, 2, 3, and this is 1, 2, 3, 0, 0, 0, 0, 0, 0, okay? And what you end up seeing is the following, okay? You get 0 in X, right? Even going from local to global, you pick up 0 forces as you would expect. In this entry, you have 31.748 kilopounds and 265 kilopounds per inch. Kilopounds, kilograms, kilograms per inch. Okay. Right. So next comes the structure solve, right, where you have KFF times UF equals to the applied forces, PF. And for this problem, these are 0. Okay. And you subtract P of 0. Okay. And the P of 0 is not 0. It will naturally contribute to the structural deformation, from where you compute the structural displacements, generalized displacements, in fact, is KFF minus 1, PF minus P of 0 equals to, why, it's not minus, it's plus. Okay. And you end up with a solution. Okay. And the solution looks as follows. 0.01115 minus 0.03583, okay, and minus 0.00, it's very small, 0.884. Okay, this value is in inches, this value is in inches, and this value is in radians. Okay, let me recall that 360 degrees is 2 pi radians, right? So 1 radian is 360 degrees divided by 2 pi. Still quite small. Okay. Good. All right. Let me take you through a couple of more calculations, and then we'll call it a day. Okay. So let's look at state determination. Okay. And for this one, let me direct you to pages 517 through 520. Okay. Okay, there are a few elaborate plots, right? But just to point a few things out. So let's look at element B. Okay, so first thing, as you recall, all right, you use the okay, this was node 2, this was node 3, right? This was our element B. Okay, and so you go and you take the solution here, right? U1, oops, U2, and U3, right? And you put them in to the delta B. Right? So you get .01115, 1115. Okay, you just copy the solution to the appropriate location, 0.03583. Okay, then you have the rotation, 0.0008840. Okay, and then at the other end you have nothing, right? It's fixed. Okay. Then you develop the delta prime, right, by taking the rotation matrix. Sorry, it's element B. Times delta B. Okay. Now remember, for this example, this is identity 6 by 6. Okay, so the two are the same, right? And then you extract the nodal forces. Okay, F prime, right, for element B will come from two contributions. You get K prime for element B, delta prime for element B, which we just did. Okay, extracted that from the solution, plus whatever you added as the vector of equivalent forces. Okay, and so this contribution looks like this: 15, 8982 minus 1, 1075 minus 166 0087 minus 15 8982. Okay, 1.1. This is why it's really not so easy to work with real numbers by hand. 75 and then 99 7829 with a negative 7829, like this. Okay, so this will be the force vector produced by just the movement of the end nodes. Okay, plus the force vector due to the applied load, 15 600 0 15 minus 600. Okay, this is that contribution. Okay. And so as a result, right, you also want to break up, okay, your axial force, okay, into two parts. So there's one that's coming here, right? Okay, and you see, right, because the motion of the end nodes gives you the axial force. That's a constant, okay? And you see that you have something that's 15.8982 this way, right? And negative 15 15.8982 this way, okay, plus, okay, you go for the contribution from the distributed load, but in that element there is no X load, okay, so you get 0. Right, so as a result, you conclude that the element is in compression. Okay. Minus, right, it's compressed. And the magnitude of compression is 15.8982 kilopounds, like this. Okay, good. Okay, so next, let's look at the moment. So this part is interesting because, again, now you have real two contributions. Okay, one coming from the motion of the end nodes, okay, produce for you something like this. And then you have another contribution that's coming from a distributed load. Okay, and so again, here you need to think, right? If it's just end nodes that are moving, right, remember that your moment is distributed linearly over the axis of the beam. Okay, and so you draw the element. Okay. Right. You look at the entries of this vector. Okay, get minus 166, right? It means that you have a clockwise moment of 166.01 acting this way, okay? You look at this entry, you get minus 99.78. Okay, minus, right? Minus is clockwise. Okay. 99.78. Okay. This way. So the moment on the left is making it concave, right? Sorry, convex, right? Locally. The moment on the right is making it concave. So you get a distribution of the moment that looks like this. Concave. Sorry, convex and concave. Okay. This is from the motion of end nodes. Okay. Then you also have the action of the distributed force. What do you see there? Right. You see 600. Okay. Plus. Okay, so what's going on, right? Counterclockwise, 600. Okay. And here you have negative 600, right? Clockwise. Okay. You have a quadratic function, right, where this part of the beam wants to be concave, then this part wants to be convex, okay, and this part wants to be concave. Okay. And so now we go, right, and combine this action, okay, that is due to end node motion, right, and this action that is due to distributed load. Okay. So on the left side, you can see that the two moments counteract each other. So then we're going to have to go to take this and subtract that one. Okay, so here's our element. Right, you have this plus this equals 2. Okay. Right. You have minus 433 here, 0.99, right, which is exactly the difference between 600 that wants to make it concave and 166 that wants to make it convex. Okay, on the one side, right? The 600 here wins out. Okay. So you have something that is concave, right? Goes into convex, right? And here you have two moments contributing together. Okay, 600 plus 99, right? 78 to make it concave. So this guy becomes 699.78, right? So when the curve goes, it shoots up there. Okay, and you get a situation like this, basically, okay, where this guy is concave, this is the convex region, okay, this is the concave region again. So this is the final distribution, okay, of the bending moment. Of bending moment. Okay. All right. So now if you start on page 521, okay, you can also compute support reactions. Okay. You do this from considerations of equilibrium between applied forces, right, coming from elements, attached to the supports, and reactions at supports. Okay. Right. And so if you follow the developments on pages 521 and 522, right, you find that P4, which is the X force at node 1, right, becomes 15.8982 kilopounds. P5, right, 47.3887 kilopounds, right, the bending moment, P6, okay, is 295, 2429 kilopounds, okay. This was node 2. And then at node 3, you find that P7 is minus 15.8982 kilopounds. P8 is 16.1075 kilopounds, and the moment P9, okay, is minus 699.7829 kilopounds per inch, and that data is at node 3. Okay. And so in your homework, okay, I want you to set up and solve this problem, right? To test your MATLAB code. Using this problem. And basically, these are the support reactions I'd like to see at the output. Output. Okay. So the way I want you to structure your code is exactly as you did with the trusses, right? You wanted to decompose the DOFs, right? DOF decomposition. Okay, which will lead to something like this. KFF, right? KFD, KDF, KDD, UF, UD, okay, equals to PF minus PF0, which PD okay, minus PD0. Okay, you may ask, well, what is PD0? PD0, right, is going to be a contribution, right, of the applied forces, okay, like the distributed loads or temperatures, for example, right, to the degrees of freedom where the displacements are prescribed, okay. And so everything is done through IDs, it's automatic. Okay. And so first, right, as a step 1, you're going to solve for UF, okay, and looking at the equations, right, you're going to find that this is going to be KFF minus 1, right, times what? Times PF minus PF0 minus KFD times UD. Right? This is going to be a first step. Okay, once you have UF, your second step is then going to be the computation of the support reactions. Right? It's going to be PD. Okay? And PD will have 3 parts. Right? It's going to be KDF times UF, which you computed from the previous step, plus KDD UD, okay, which is coming from the motion of the supports, right, and minus, or sorry, plus PD0, okay. This is going to be the contributions of distributed, from the distributed loads, okay. And so if you implement this procedure in your code, just like you did for the truss element, you should be able to solve all the problems that I asked you to do by hand. This way you verify your code, and once you verified your code, you can move on to larger structures. Okay, and so at this point, we're done with Professor Conte's reader. And now we're on to dynamics. that's it for this lecture, and then wait for me to upload more lectures.